Welcome to all. In the previous video, we were looking into the concept of curves in E3, and we have defined the curve in E3 in terms of a locus of a point. The point P is seen in terms of position vector OP. Now we will see the formal definition of curve in E3. So definition says a curve in E3 is a differentiable function alpha from I to E3, that is from an open interval I into Euclidean 3 space E3. So this is how a curve is defined formally in terms of a function. We have seen examples in terms of locus. We have seen straight line equation and helix, right circular helix equation. So let's view them in terms of functions. So we are seeing them again in terms of functions. So straight line is simplest type of curve. In the Euclidean space. Its coordinate functions are linear. Means there is no square term. That is, the variable is not of the type square. So we can write the straight line equation explicitly as it is a curve alpha from R to E3. Here we are taking I as the real number system R, such that alpha of t is equal to p plus tq. We can observe it is depending upon a single variable t. So this can be written in terms of order triplet: p1 plus tq1, p2 plus tq2, p3 plus tq3, such that the point q is not equal to 0. So this is the straight line. Passing to the point P, which is obtained by putting t is equal to 0. So P is equal to alpha of 0, which is in the direction of the point Q. Thus any straight line passing through the point P in the direction of Q is given in terms of a function alpha from R to E3, such that alpha of t is equal to p plus tq. So it is depending upon a single variable t. So we will see another example, which was the right circular helix in terms of function. Right circular helix. Here it is given in terms of function as it is a function alpha from R to E3, such that alpha of t is equal to a cos t, b sin t, bt, with a as greater than 0 and b is not equal to 0. This curve, which is a right circular helix, is obtained from the curve obtained from a curve alpha from R to E3 such that alpha of t equal to a cos t, a sin t, 0, which is nothing but a curve traveling around a circle with radius a greater than 0, which is in the xy plane. Here, in order to get the right circular helix, which is given in terms of a cos t, b sin t, bt, we have to rise the curve alpha of t is equal to a cos t, a sin t, 0 along a z direction. So we should allow the curve alpha of t is equal to a cos t, a sin t, 0 at a constant rate along the z direction. Hence, a right circular helix is obtained by rising the circle which is in the xy plane along the z direction with a constant rate. So, this is about how the right circular helix is obtained. Now, we have to shift into another concept. Before that, we will observe one thing. So, we can visualize a curve alpha in E3 as a moving point, then at every time, at every instant time t, there is a tangent vector. At the point alpha of t, so which gives the instantaneous velocity of the curve alpha at that particular point. As curve is a locus of a point, therefore for each moment there is a tangent vector we can draw. So that tangent vector gives the velocity which is instantaneous, means at that point. So that curve, that vector will give the velocity at that instant of time. So this leads to the concept of velocity of a curve. Let's see the concept of velocity of a curve. The definition says we should have a curve. So let alpha from I to E3 be a curve in E3 with the point alpha as alpha equal to alpha 1, alpha 2, alpha 3. Now for each number t, means each time interval t, each time instant t, in the interval I, the velocity vector, as velocity is having direction, therefore we can write the velocity vector of the curve alpha at the time t is nothing but the tangent vector, which is given by alpha dash of t is equal to d alpha 1 by dt at the time instant t, d alpha 2 by dt at the time instant dt, d alpha 3 by dt at the time instant t. So this is the velocity vector of the curve alpha at the time instant t. So how it can be proved? Let's see. We have to prove the tangent vector is equal to alpha dash, which is given in terms of derivative of alpha 1, alpha 2, alpha 3 with respect to t at a time instant t. So let's see the derivation, how it is going to work. First we will consider alpha of t is equal to alpha 1 of t, alpha 2 of t, alpha 3 of t. So in order to find the derivative of curve alpha, we will use the definition of differentiation of a function, which is given in terms of since df by dt at a time instant t can be given by as limit of delta t tends to 0, f of t plus delta t minus f of t by delta t. We can apply this formula to the coordinates of alpha by varying t to t plus delta t. So for each coordinate we have to apply the same thing, means the difference between the function value at the t plus delta tth instant and the tth instant. So we will get alpha of t plus delta t minus alpha of t divided by delta t. This is equal to, for each coordinate it will follow alpha 1 of t plus delta t minus alpha 1 of t divided by delta t. For alpha 2 the same, t plus delta t minus alpha t by delta t. Similarly for third coordinate, t plus delta t minus alpha 3 of t divided by delta t. Now as we are taking delta t tends to 0, we will take delta t tends to 0. Then we get limit as delta t tends to 0, we will get alpha dash of t is equal to d alpha 1 by dt at a time instant t, d alpha 2 by dt at a time instant t, d alpha 3 by dt at a time instant t. This is how just differentiating the curve alpha with respect to t will give the velocity vector of the curve at the particular time instant t. So this is about how to find the velocity vector of a curve. Let's see some examples so that how to find the velocity will be clear. Examples. As we have taken the famous curves, most well studied curves, the first one is straight line. We are studying velocity of a straight line. Yes, we have straight line equation is alpha is a function from I to E3, I is equal to R, such that alpha of t is equal to P1 plus TQ1, P2 plus TQ2, P3 plus TQ3. Just we will differentiate the curve alpha with respect to t. We have alpha dash of t is equal to Q1, Q2, Q3. So this is the velocity of the straight line, which is obtained by differentiating the curve alpha with respect to t. So this is how we can find the velocity of the straight line. Now we will see the second example, which is for velocity of helix, velocity of right circular helix. So as we know that the equation for right circular helix is, it is nothing but a function from R to E3 such that alpha of t is equal to a cos t, a sin t, bt, such that alpha is greater than a is greater than 0 and b is not equal to 0. Just differentiating alpha of t with respect to t will give the velocity of right circular helix. So alpha dash of t is equal to minus a sin t, a cos t, p. So this is the velocity of the right circular helix at the time instant t. So we can observe one thing from both velocities of straight line as well as the right circular helix. We can note them separately. So we have a note. First one is for straight line. So we can see the velocity vector of straight line contains constant term only. So therefore we can infer that all the velocity vectors are parallel because it is a straight line. So at each point, if it add tangent vector, all of them will be parallel, and only the point of application changes as t changes, which is in case of straight line. So also from the velocity of right circular helix, we can see the z coordinate is constant. So this shows that the helix, which is the right circular helix, rises constantly. Which can be inferred from the fact that the z coordinate of alpha dash of t is a constant. So what these two will tell is that, so we can say straight line is a line which is going in one particular direction. So at each point of a straight line, if we draw a tangent vector, all of them will seem to be parallel. Hence, in case of straight line, if the point is moving, means the locus of the point is changing, but the tangent vectors are remaining parallel. Therefore, all the velocity vectors are parallel, but only point of application changes as the time lapses. This is for straight line. In case of right circular helix, so after finding the velocity vector, we can observe that the z coordinate is constant, which says that the helix is constantly rising along the z direction or along the z coordinate. So this is about the velocity of straight line and right circular helix. We will see next concept, which is called reparameterization of curves, in the next video. Till then, keep watching. Thank you.